Okay, so today we are going to study how to find out the lattice parameter. Okay, and lattice parameter is the dimension of the unit cell. Okay, so to find out the dimension of the unit cell or to investigate the inside the materials, actually to see something we need light. Okay, without light you cannot see anything. Suppose you are in a dark room, but the object that you are looking at, if that is in a room which has got plenty of light, you will be able to see. However, if the object is in the dark room and you are in a broad daylight place, you will not be able to see that thing. So that means to see something we need light. So the science of vision is basically light falls on a material, and then light will be reflected from the surface or all parts of the material, and then it will make an image on the retina. Okay, and on the retina has got some photosensitive stuff. Okay, and that will create some signal, and that signal will reach to the brain, and then brain will analyze. Okay, image processing. Brain will do the image processing, which you are going to study in your third year or fourth year of BSc engineering. So brain will analyze all these electrical signal, and then finally it will make an image, or it will give you an understanding that if I look at Jamaluddin from Afghanistan, so I will see, oh yes, this is Jamaluddin. Okay, when he switch on his camera, I see like this. Or if somebody A switch on camera, that is how it gives an image, or that is how we see you. Okay. Now to see the inside of the material, this is the whole electromagnetic spectrum. Okay, starting from 1 hertz to 24 hertz. Okay, that means starting from long radio waves to gamma rays. Okay, and that's the top scale is the frequency, and bottom scale is the wavelength. Look, where the frequency is less, wavelength is high. It's 10 to the power 9 meter. 10 to the power 9 meter. 10 to the power 9 meter means 10 to the power 9,000 meter means 10 to the power 6 kilometer. 10 to the power 6 kilometer means 1 million kilometer, which is quite big. Okay. Okay. So now to see an object, to see to investigate the materials, we need to find out the information from atom, and we know the atomic dimension is of the order of here. It's of the order of 10 to the power minus 10 meter. Okay, it's like we are here. So to see atoms, or to know information about atom, we need to send some light whose wavelength is comparable to the size of the atom. Okay, so when we have seen in crystalline solid, atoms are arranged in regular and periodic manner. Okay, so it has got some interatomic spacing. It's like that. Interatomic spacing, and dimension of the interatomic spacing is also like that. Okay. So that is why we need X-ray to investigate, to get the information about atom. I think it is clear to you. So why we need X-ray to get the information about atom? Because the dimension of the atom, or dimension of the interatomic space, is comparable to the size, we need wavelength of light comparable to that dimension. Okay, and that is in the X-ray range. So X-ray has got soft X-ray and also the hard X-ray. Okay, X-ray with lower frequency is called soft X-ray, and higher frequency is called hard X-ray. Okay, so we need intermediate range of X-ray to investigate the atoms. Now, what will happen? You have studied in your first semester in your optics that when light or electromagnetic wave pass through a narrow opening, okay, so it can pass through it if the wavelength is comparable to the opening, and so in addition to passing, it will spread. It will spread on the other side, and this spreading of light beam is called the diffraction. Okay, so when we analyze or investigate materials with X-ray, we call it X-ray diffraction. Okay, because of the spacing is the distance between the parallel plane of atoms. Okay, and so a crystal can be considered as when it has got small opening, we call it grating. So crystal can be considered as natural grating. Okay, so we need X-ray to investigate the atomic level of a material, and over there X-ray diffraction occurs. Now, if X-ray diffraction works, so this is the this is our our materials, or the other one, the same thing. We have shown two planes over here, and this and this in this figure three planes: A plane, B plane, and then C plane. Okay, so these are crystal planes, and we have studied earlier the parallel plane has got the same. This is a plane, so plane pass through your desk or pass through your floor parallel to that one. Okay, this is one plane, that one is another plane, and another plane, and all this plane has got the same Miller indices H. We choose H, K, and L. When light X-ray falls on on the top surface, okay, with an angle theta, which is called Bragg angle or grazing angle. Okay, so according to the laws of light, it will also, if this angle is theta, so that angle will also be theta with the plane. Okay, and then and another beam parallel to the top one will pass through the interatomic space, and then it will reflect from the inner plane. Okay, and again, if they are parallel, so this angle is theta, that angle will also be theta. Okay, now if this angle is theta, that angle is theta, then okay, now we need to find out the these two ray or other ray also reflect from the bottom plane, and these rays do not travel the same path. Now we are interested to find out the path difference. So to find out the path difference, these two beam, we're gonna draw the perpendicular. Look, we draw the perpendicular, PS perpendicular and PT perpendicular. Now, up to this perpendicular, that distance from the left, this distance are same, this distance are same. So path difference between two beam is actually in this figure is SQ and QT. If you look at this figure, this will be MH double prime and then PH double prime in this figure. Okay, so that is all written. So path difference is basically MH double prime P, which is MH double prime plus PH double prime, or in this case, it is SQT or it is SQ plus QT. Okay. Now, the spacing between the two parallel planes, we define it by DHKL. HKL is the Miller indices of that plane, D. Okay. Now, if this is D, and we can show that this angle will also be theta and this angle will also be theta. If this is D and this angle is theta, this SQ or QT, or in this case MH double prime and PH double prime will be D sin theta. So one is D sin theta plus another is also D sin theta. So total path difference will be 2D sin theta. From our optics knowledge, we know that if this path difference is integral multiple of the wavelength of the incident beam, incident X-ray, then what will happen? Constructive if we place a detector over here, constructive interference will occur. What does constructive interference means? Constructive interference means here, if you place a detector, the intensity of the light will be very, very high. Okay, so that's the constructive interference. Okay, so what we this is called Bragg's law of X-ray diffraction. And next slide shows the typical X-ray diffraction, X-ray diffractometer. So X-ray diffractometer basically consists of, here is an X-ray source, we need an X-ray source, and then a detector which will detect the reflected light. Like when we see an object, so we need a light from the sunlight or our room light or a torch light, and here is our eye. Eye is, in our case, eye is the detector. But in X-ray diffractometer, you need an X-ray source because your torch light cannot produce, or your room light cannot produce X-rays. So you need an X-ray source, and you need a detector to reflect, to detect the reflected light, and also you need the materials that you are going to investigate. That's the one. So these are the three parts. This is the X-ray source, and this is the detector over here, and that's the material under investigation. Look, so this is the surface of the material, and it incident light incident with an angle theta. Okay, and this is the original direction of the light, and this is the angle. So this angle is theta, and this angle will also be theta. So we place the detector with 2 theta with the original direction of the X-ray, and this sort of scan is called theta to theta scan. Here I showed 2 diffraction, X-ray diffraction pattern of my own sample. So this is from my own research. So I made the polycrystalline. You know what is polycrystalline? Polycrystalline barium iron tantalate. Okay, this is one kind of multiferroic materials which you may study when you do some research in your graduate or postgraduate level. Okay, so this barium iron tantalate are sintered means heat treated at various temperatures. Well, black one is 1200 degrees Celsius, 1300 and 1400 degrees Celsius. And you can see that look, so when X-ray are incident on these materials, the same material, sintering temperature is different only. So no X-ray at 10, 15, 20, no X-ray diffraction is, no Bragg's law is satisfied. That is no high intensity there. So this is the breakdown intensity. However, when it reaches about 34 or 32 or 33 degrees of 2 theta below, then X-ray, then Bragg condition satisfied. So over here, detector detects very high intense light. Okay, and this is from 110 plane. Now you know what is 110 plane. I hope you will be able to draw 110 plane if I ask you to draw in the exam. And then again, no Bragg condition is satisfied. Another Bragg condition is satisfied at 111 plane. And then finally 200 plane, because it's a polycrystalline materials. Polycrystalline material consists of various single crystal with different orientation, which we have studied earlier. Okay. However, look, if I make this material as a single crystalline, what I did, I took a single crystal substrate, strontium titanate substrate with 100 orientation, and then if I deposit these materials, barium iron tantalate, by this one machine is called pulsed laser deposition technique, or in brief, it is PLD technique. Then a single crystal will be, materials will be grown on top of 100 symmetry. Okay, so this is called thin film or single crystalline thin film. So in this case, orientation of the atom will be same. So we got one, no Bragg condition is satisfied over here. Look, in this case, materials are well ordered very nicely. So that is why the peak intensity is very high and very sharp. Okay, so we got one Bragg condition from 100, and then about double of the angle we get another 200. And previously we have studied 100 and 200 plane are parallel plane, and this intense peak is from the substrate, because substrate is very thick, so intensity is also very high. And then if we go further about 66, we're gonna get 300 peak, and then if you go further, and then 400 peak, and we know 100, 200, 300, 400 peaks are parallel are from parallel planes, okay, or similar planes. However, what would happen if you have a this is for crystalline solid. You know the crystalline solid is two types, single crystal. So this sort of X-ray will be there. Polycrystal, this one. What about the polycrystalline materials? Sorry, what about the amorphous materials? If you have an amorphous materials, and if you plot 2 theta and then intensity, it will be no Bragg condition will be satisfied. Okay, so it does the background line, but sometimes, as we have mentioned, some short range periodicity may observe. So sometimes you may get a broad peak, or you may get nothing, just the background peak, because no Bragg condition is satisfied. Okay, if you do the X-ray for amorphous material, this is the X-ray for amorphous material. Okay, that's one. Okay, so now what information do you get from X-ray diffraction? X-ray, actually, we do X-ray diffraction to determine the crystal structure, to see the atomic arrangement. Like from the X-ray diffraction pattern, at first we can estimate whether our material is amorphous, if this sort of X-ray diffraction is amorphous, or crystalline. If it is crystalline, then it can be polycrystalline, or it can be single crystalline, like that. Okay, so now from the X-ray diffraction peak, suppose here is the X-ray diffraction peak, and D and 2D sin theta and lambda. From here you can find out this theta C, okay, where the intensity get maximum, theta C. You know, the n is the order of distribution. Like in previous case, we have found 100 peak, and also the 200 peak, 200 peak, and I also mentioned about 300 peak. So these are the basically the order of the diffraction. In this case, n equal to 1. In this case, n equal to 2. And this case, n equal to 3. So you know the order of the diffraction, and then wavelength of the X-ray, incident ray, and you know theta C. Then you will be able to calculate D. What is D? D is the interplanar spacing that I have already mentioned. Interplanar spacing. So here I showed again incoming X-ray, beam number 1, beam number 2, outgoing X-ray, beam number 1 and beam number 2, and these are the path difference, extra distance, because these extra distance, these extra distance is traveled by the wave number 2, and due to that, and this is the interatomic separation. Okay, so which I have mentioned earlier. So from this, from the X-ray diffraction, we get D. Still, we don't know how to calculate the lattice parameter A, B, and C. Okay, so we need to do some further studies. Okay. This is the typical X-ray diffraction pattern for iron. BC, iron, you know the iron is body centered cubic. You do the X-ray. So look, some no X-ray, no Bragg condition will be satisfied. But however, at 45 degree, around 45 degree, Bragg condition is satisfied. And this is from 100 peak. And how does 100 peak look like? This is the 100 peak. Okay. And then again, if you increase no Bragg condition, and it will be Bragg condition will be satisfied at 200 peak. How does it look like? It will look like that. And then if you increase further, so about 82 or 3, you will get 211p, and 211p look like that. Okay, I believe you understand it nicely. Okay, so as we have mentioned, to find out the lattice parameter, we need to do some further work. Okay, further work is we need to find out the relationship between interplanar distance D with the Miller indices via a. We need to find out relationship between interplanar distance and ABC via Miller indices. Okay. We draw 2 unit cell over here. Okay, and we draw the ABCD plane and also EFGH plane. ABCD crystal plane and EFGH crystal plane are parallel planes. And we know the Miller indices of this plane. So there is an intercept, one intercept on x-axis, one lattice constant intercept on b-axis, and it is parallel to the z-axis. That means Miller indices of this one, if it is Miller indices of this plane will be 1, 1, 0. One will come from one lattice constant, and infinity lattice constant. And if you take the reciprocal, so that infinite will give you 0. Okay. And distance between these two planes basically will be this one, because another plane will pass through the origin, like this one, it pass through the origin. So distance of this plane is basically that one. So we can actually find out the interplanar distance of this kind for this set of plane very easily, because if it is cubic, that distance is root 2a, because this side will be a, this side will be a, so this will be root 2a. And this plane is passing halfway. So the interplanar distance between these two planes will be just half of root 2a, which is half of root 2a, which is basically a by root 2. However, in this section, we are going to derive a general relationship which will connect any crystal planes with any lattice parameters via Miller indices. Okay. Now this 100, this is the Miller indices. So one index is denoted by H, and this is K. Second index is K and L. Okay. So HKL. So this HKL value actually comes from the reciprocal of the intercepts. So in this case, intercept is OB, and their reciprocal is actually H. So we can write OB equal to A by H, and similarly we can write OC equal to B by K, and similarly OP, which is actually infinite, OP will be C by L. L comes from the Miller index from the intercept of z-axis. Okay. Now, to find out the distance, perpendicular distance from origin to the plane, to any plane, not this plane, we're going to find out a general relationship. So, perpendicular distance from the origin to the plane represents the interplanar distance d of these families of planes. And let the direction of cosines of this perpendicular distance OL be cos alpha prime, cos beta prime, and cos gamma prime. This alpha prime, beta prime, gamma prime are different from alpha, beta, gamma, and we have already mentioned alpha, beta, gamma are the interfacial angles. That means the angle between various crystallographic axes. So in this case, if you draw a perpendicular from the origin to the desired plane, so it will have a projection on x-axis, projection on y-axis, and projection on z-axis. That projection or direction of cosines are denoted by cos alpha prime, cos beta prime, and cos gamma prime. Okay, so we have already denoted OB is A by H. Now, what would be the cos alpha prime? Cos alpha prime is the this direction of cosines on x-axis. So it will be D by OB, and for y-axis it will be D by OC. For z-axis it will be D by OP. So we know OB, OC, OP. So finally, cos alpha prime will be D by OB. Substitute the value of OB, which is A by H. So finally, it will be DH by A. Similarly, cos beta prime will be D by OC. And if you substitute the value of OC, it will be DK by B. Similarly, cos gamma prime will be DL by C. Now, you have studied in your trigonometry or geometry classes cos square alpha prime plus cos square beta prime, this will be beta prime, cos square gamma prime equal to 1. So use this relationship, it will give you d square h square by a square, d square k square by b square, d square l square by c square equal to 1. If you take d square common, it will be h square by s square, k square by b square, plus l square by c square equal to So from here 1 by d square will be this. 1 by d square will be h square by s square plus k square by b square. So this is the general relationship which connect all 7 different crystal system with 7 sets of lattice parameter A, B, C via Miller indices H, K, and L. So this is the general formula which is valid for any type of crystal system. However, we have studied cubic crystal system in detail. So in case of cubic crystal system, A, B, C are equal. If we substitute the A, B, C are equal and that is equal to A, so it will be 1 by d square. So it will be basically 1 by d square, and in the denominator it will be all will be A S square. So it will be, because S square, B square, C square all are equal. So finally it will, on the numerator it will be H square plus K square plus L square. So that's the relationship for cubic crystal system. And for this, for the plane that we have considered earlier, for this plane HKL is H equal to 1, H equal to 1, K equal to 1, L equal to 1. If you substitute, so it will be 1 square plus 1 square plus, sorry, L equal to HK, L equal to 0. So it is 0. So finally it will be 2 by S square. So D will be basically from here A by root 2, which we have predicted earlier. That means the equation that we have derived is very correct one. Okay. Now we can find out. So from our today's discussion, from Xray diffraction pattern, we can find out D, and if we know D, then we can calculate if it is cubic, we can calculate lattice constant A, and if it is any other crystal, if we choose if a polycrystal element, if we choose 3 different peaks, 3 sets of Miller indices, then by solving simultaneously 3 different equations, we can calculate A, B, and C. So now, if you know A, B, and C, or if you know A in case of cubic parameter, cubic crystal system, then you can calculate atomic radius, and then you can calculate packing factor, you can calculate planar density of atom, you can calculate linear density of atom, you can calculate density, everything. That means the knowledge about crystallography is completed now. So that means that's the end of our crystallography chapter. Now to check your understanding, here there are some problems. And you should be able, if you understand our previous chapters lessons, then you'll be able to calculate these problems. Okay, let me solve you the first problem. Lead crystal. What is the crystal nature of lead? I may ask you in the exam, although I tell you over here. Crystalline nature of lead is FCC. So I may ask you to draw a typical unit cell. So typical unit cell will be like that. For FCC, it will be this one. So atoms will be located over here. All the atoms will be located at the corner, and also at the there will be another atom at the center of the faces, center of all faces. So I gave only 3 faces, okay, and behind face and this face and the bottom face, behind that one and that one. Okay, so that's the typical unit cell of face centered cubic crystal. Now in this problem, atomic radius is given 0.17. It is FCC. Atomic radius given. So you can easily calculate A from the A will be, in case of FCC, 4A equal to root 2A. So A will be 4. So actually 4R equal to root 2A. So A will be 4R divided by to 2. So from this relationship, you can easily calculate A. So you find A. Now your task is to calculate number of atom per square millimeter, or so you can express A in millimeter by multiplying it by suitable number. Okay, so you get A in millimeter. Now what is the area of 100 plane? 100 plane is this front plane. 100 plane is the, if I draw individually, that's the 100 plane. Atoms will be located at the corners, and also atom will be located over here, and atom will be located over there. And what is the area of 10 plane? Both sides are A. Area will be S square. And if you express A in millimeter, so area will also be in millimeter square. Now, in this millimeter square, how many atoms are there? So this central atom is fully lies in this plane. Okay, and from the corner atom, the contribution will be 1/4, 1/4, 1/4, 1/4, another 1. So number of atom in 100 plane is actually 2. Okay. Now two atoms are S square plane. S square area contain S square in millimeter square contain 2 atoms. So 1 millimeter square contains 2 divided by S square. And if you calculate 2 divided by S square, that will give you this is the answer, 8.17 or something like that. So approximately it will be 8.2 into 10 to the 12 atom per square millimeter. So you can see it's a huge number. 1 millimeter is the thickness of your nail. Okay, and in that thickness of your nail contains okay, thickness of nail contains this number of atoms. Millions of atoms. 10 to the 12 means million of atoms. Okay. I hope you will be able to solve this problem. Like, okay, number 2. X-rays of unknown wavelength are diffracted with this angle, with lattice constant A is given. And separate determination indicate that this diffraction line for copper is the first order, n equal to 1. Okay. So for D11. So you know lattice constant is A, okay, and 2 theta is given, and from 2D sin theta, you are asked to calculate the lambda wavelength. Okay, from D11, A is given, D11, you can calculate the value of D. How are you going to calculate the value of D? Because we know the relationship 1 by D square equal to H square plus A square plus L square divided by S square. So you know A, you know HKL, it is 1 plus 1 square plus 1 square plus 1 square. That is 1 plus 1 plus 1. So this is known, we'll be able to get D. Once you know D, then 2D sine theta equal to n lambda. And it is first order, value of n equal to 1. So it's just lambda. So lambda is 2D sine theta. You know D from here, and theta will be half of this angle. This is 2 theta, half of this angle. Then you can calculate lambda. So that's the way. And then lattice constant is given here. And what is D220? Find out D11. We already calculated what is D11. F is given, and then D200. Okay. So D200 is actually a half plane. So if you have a 100 plane and half of the axis, along the half of the axis, that plane is called D220. Okay. So, I hope you'll be able to do that. And then if I solve number 7, so potassium chloride is a face-centered cubic crystal having density this 1.98 gram per centimeter cube. And if its molecular weight is this, calculate the distance from one atom to the next atom of same kind. That means distance from the one atom to the next atom. Potassium chloride has got sodium chloride like distance. One atom to the next atom of the same kind means you are asked to calculate A. And the distance between the adjacent atoms. In this case, distance between the, if you remember that one atom, similar atom are there, and in the half plane there is another atom. Okay, face center giving now. So half distance between the adjacent atom is half of the lattice constant. So at first we will calculate A, density is given, atomic weight, molecular weight is given, you can calculate density because our density formula is, if you remember, rho equal to 1 by A cube, and then N is the number of atom per unit cell, if you remember, Ma divided by Na. N is the number of molecule per unit cell. So it's a potassium chloride, which is sodium chloride like this. That means 4 molecules will be there. That means 4 potassium chloride molecule, or 4 potassium atom, or 4 chlorine atom will be there. And Ma atomic molecular weight is given there. N is the Avogadro's number. A is given. Rho is given here. From there you can calculate A. Once you know A, that's the answer of this first one. And answer of the second portion is half of A, and so on. This one is interesting. A plane intercepts on the crystallographic axis at one lattice constant at x-axis, 2 lattice constant, and y-axis 1 lattice constant at z-axis. What are the Miller indices? So we will take reciprocal. So reciprocal of 1 is 1, reciprocal of 2 is half, and reciprocal of 1 is 1. And then convert into integer. So to convert into integer, 2, 1, and then 2. That would be the Miller indices, and so on. Okay. So that will be homework. All these will be homeworks. So that's the end of our today's